Have you ever looked up at the night sky and wondered what holds it all together? What if I told you that everything we can see, the stars, the galaxies, the shimmering cosmic spectacle, makes up less than 5% of the universe? The rest is something we can't see, can't touch, and barely understand. Yet this invisible force is the very scaffolding of reality, an enormous cosmic architecture known as dark matter. It's the hidden framework that binds our universe, whispering secrets about existence itself. Imagine for a moment that you're floating in the depths of space, surrounded not just by pinpricks of light, but by an intricate, invisible web, a delicate lattice woven from something we've yet to fully grasp. This is the cosmic dark matter web, a structure so vast and mysterious that it defies everything we thought we knew about the cosmos. For decades, scientists have been chasing its shadows, trying to decode its patterns, its purpose, its profound influence on the formation of galaxies and the fate of the universe itself. And what they've discovered so far only deepens the wonder. In this video, we're setting out on a journey to explore 25 of the most captivating mysteries tied to this cosmic dark matter web. From its ghostly gravitational pull to the way it shapes the largest structures in existence, we'll uncover why dark matter remains one of the greatest puzzles in modern science, and why understanding it could reshape our entire view of reality. You're about to step into a story of cosmic scale and human curiosity, where every question leads to another, and every discovery pulls us closer to the heart of the universe's best-kept secrets. Stick with me, we're going places few have ever ventured, and I promise by the end, you'll never look at the night sky the same way again. So if we can't see it, touch it, or directly detect it in any way, how do we even know dark matter is there? The answer lies in the universe's most reliable storyteller, gravity. Think of it this way: you're in a completely dark room and you can't see a thing, but you feel a consistent, gentle tug on your sleeve. You might not see what's pulling you, but you know with absolute certainty that something is there. For astronomers, entire galaxies are that sleeve, and the mysterious tug is undeniable. This story of discovery begins close to home with our own Milky Way. The stars orbiting the galactic center move at such tremendous speeds that, based on the gravity of all the visible matter we can see, the stars, gas, and dust, they should be flung off into the void of intergalactic space. The fact that they aren't means there must be a huge amount of additional mass, an invisible gravitational anchor holding everything together. This missing mass creates a gravitational force far stronger than anything visible matter can account for on its own. But the evidence doesn't stop at individual galaxies. Look at massive clusters of galaxies and the case becomes even more compelling. These are the largest gravitationally bound structures in the universe. When we observe how these clusters behave, we see two gigantic pieces of evidence. First, the individual galaxies within a cluster move so quickly that, again, the visible mass is nowhere near enough to keep the cluster from flying apart. Second, and perhaps more visually stunning, is something called gravitational lensing. The immense gravity of a galaxy cluster acts like a lens, warping the very fabric of space-time and bending the light from even more distant galaxies behind it. This creates beautiful, stretched, and distorted arcs of light in our telescopes. The degree of this bending tells us how much mass is present, and the result is always the same. There is far, far more mass causing the distortion than we can possibly see. The light is literally being bent by the invisible. Perhaps the most profound evidence for this invisible architecture comes from the very beginning of everything, the afterglow of the Big Bang itself. The cosmic microwave background radiation is a snapshot of the infant universe, a faint microwave static that fills all of space. Within this ancient light are tiny temperature variations, hot and cold spots that are essentially blueprints for the large-scale structure of the universe we see today. These patterns tell us precisely how much ordinary matter and how much dark matter existed in the early cosmos. The calculations are clear and have been confirmed by multiple space missions. Ordinary matter makes up less than 5% of the universe's total mass and energy. The gravitational effects we see are only possible if a completely different, invisible form of matter, dark matter, is woven throughout the cosmos, providing the scaffolding upon which galaxies could eventually form. It's the hidden framework that made our visible universe possible. So if we've established that dark matter is real because of its gravitational effects, you might be wondering, what about the stuff we can see? The normal atoms, the protons and neutrons, the stuff that makes up you, me, planets and stars. This is what scientists call baryonic matter. And for a long time, cosmologists were confident they knew exactly how much of it should be in the universe based on those detailed readings from the cosmic microwave background. The math was precise and the models were clear, but when astronomers went to actually take inventory to count up all the luminous stars, the swirling gas, and the scattered dust across the cosmos, they came up short. A lot short. Nearly half of all the ordinary matter that should be out there according to our best theories was simply missing. This became known as the missing baryons problem, and it was a huge, embarrassing hole in our understanding. Think of it like balancing a complex checkbook for the entire universe. You have a very reliable statement, the afterglow of the Big Bang, that says you should have a certain amount of money in your account. But when you actually count the cash and look at your visible assets, you only find about half of it. Where is the rest? It's not hidden in a dark matter vault. This is normal matter that's just gone. For years, this was a major crisis. Had our foundational theories about the Big Bang been wrong? This is where the dark matter web enters the story, not just as a mystery itself, but as a potential guide to solving another. Scientists began to theorize that this missing ordinary matter wasn't truly missing at all. Instead, it was hiding in plain sight, or rather, in the dark. They proposed that the gravitational pull of the dark matter web, that vast invisible scaffolding, had gathered much of the universe's ordinary matter into extremely diffuse, incredibly hot clouds of gas stretching between galaxies. This material is so hot that it doesn't form stars or even cool clouds. It exists as a thin, ionized plasma, often called the warm-hot intergalactic medium, or WIMP. Because it's so spread out and so energetic, it doesn't emit light in a way our telescopes can easily detect. It's essentially invisible to most observational methods. Finding it required a new approach. Astronomers had to become cosmic detectives looking for the faintest clues. They used light from incredibly bright, distant objects called quasars as cosmic flashlights. As this light travels for billions of years to reach us, it passes through these vast, faint webs of hot gas. The gas absorbs very specific wavelengths of the quasar's light, leaving behind a unique fingerprint, a tiny, telltale dip in the spectrum of the light that arrives at our telescopes. It's like finding a single specific smudge on a giant, clean window pane. Painstaking observations, particularly with space-based X-ray observatories, have started to find these fingerprints, providing strong evidence that a significant portion of the missing baryons are indeed tied up in these immense, faint structures, guided and gathered by the relentless gravitational pull of the dark matter web they are draped across. So the mystery of the missing baryons is slowly being solved, but in doing so, it reveals an even deeper truth about our universe. The ordinary matter, the stuff we thought was the main character of the cosmic story, is really just following the stage directions written by the invisible dark matter. It's a humbling reminder that what we see is only a small part of a much larger and far more mysterious production. This gravitational paradox leads us directly to one of the most pivotal moments in modern astronomy, a discovery so fundamental it forced us to rewrite our understanding of the cosmos. For centuries, we operated under a simple assumption guided by the laws of Kepler and Newton. Just as the outer planets in our solar system orbit the Sun more slowly than those close in, the stars at the outer edges of a galaxy should orbit its center much more slowly than those near the core. The vast majority of a galaxy's visible mass, its stars and glowing gas, is concentrated in the bright central bulge. The gravitational grip of this central mass should weaken with distance, meaning those distant stars on the galactic frontier should be drifting along at a leisurely, declining pace. But in the 1970s, a brilliant astronomer named Vera Rubin, working with her colleague Kent Ford, decided to put this assumption to the test. They meticulously measured the rotational speeds of stars in the Andromeda Galaxy, our nearest major galactic neighbor. They expected to see those outer stars slowing down like cars on a far-off racetrack, barely keeping momentum. What they found instead was utterly shocking. The stars far from the galactic center were not slowing down at all. They were orbiting at nearly the same tremendous speed as the stars closer in. It was as if every car on that racetrack, regardless of whether it was on the inner lane or the outer lane, was somehow hurtling along at exactly 100 miles per hour. This flat rotation curve, as it's called, defied every prediction based on the laws of gravity and the amount of visible matter. The implication was staggering. For those outer stars to be whipping around at such high speeds without being flung off into the void, there had to be a tremendous amount of additional mass, invisible mass providing the extra gravitational glue to hold them in their orbits. This mass couldn't be concentrated in the center. It had to be distributed in a massive spherical halo that enveloped the entire visible galaxy, extending far beyond the reach of its outermost stars. Vera Rubin's work provided the first direct, incontrovertible evidence that galaxies are overwhelmingly composed of something we cannot see. Her discovery of the galaxy rotation problem didn't just suggest dark matter might exist. It proved that our universe is filled with a mysterious, dominant substance that governs the very motion of galaxies. It was a humbling and revolutionary correction, showing us that the glittering stellar cities we admire are merely the illuminated tips of vast, invisible icebergs. But if the rotation of galaxies gave us powerful indirect evidence, scientists craved something more. A direct visual demonstration that dark matter was not just a mathematical fix, but a physical substance that behaves in its own unique way. They needed a cosmic experiment, a massive collision where the rules of physics would play out on a grand scale. And in the late 1990s, the universe provided just that, a spectacular, violent clash of galaxy clusters known as the Bullet Cluster. This was not just another deep space image. It became one of the most compelling pieces of evidence for dark matter's existence, a snapshot of a cosmic car crash that separated the visible from the invisible. Picture two enormous clusters of galaxies, each containing hundreds of galaxies, vast clouds of multimillion-degree gas, and an immense amount of dark matter. They plowed into each other at a staggering speed of millions of miles per hour. The resulting system is named the Bullet Cluster for the bullet-shaped shock wave that formed in the aftermath, a clear indicator of the immense forces involved. For astronomers, this wasn't a tragedy, it was a perfect natural laboratory. They could observe how the different components of these clusters, the stars, the hot gas, and the dark matter, reacted during this incredible collision. And react they did in completely different ways. Let's start with the stuff we can see. The galaxies themselves, both the individual stars and the dark matter halos surrounding them, are mostly empty space. During a collision, they act like two swarms of bees passing through each other. There's so much space between each bee that they barely interact. They simply coast through the collision and continue on their way, emerging on the other side largely unaffected. The hot, X-ray emitting gas between the galaxies, however, is a different story. This gas is a tangible, viscous medium. During the collision, the clouds of gas from each cluster slam into each other, creating immense friction and pressure. This gas gets stuck in the middle of the collision, much like two clouds of smoke would merge and swirl together if you blew them into each other. It heats up even more and glows brightly in X-rays, marking the center of the cosmic wreck. Now, here's the crucial part. Using the technique of gravitational lensing, astronomers could map the total mass distribution in the cluster. They could literally weigh the entire system and see where the mass was concentrated. The result was astonishing. The map revealed that the vast majority of the mass, the source of the gravity, was not centered on the glowing cloud of hot gas in the middle of the collision. Instead, the gravitational mass was located way out where the galaxies had sailed through, perfectly aligned with their positions. This meant that most of the stuff providing the gravity had, like the galaxies, passed right through the collision without slowing down. It had become separated from the normal matter. This was the visual proof. The normal, baryonic matter, the gas, got caught in the crash and was left behind. The dark matter, which doesn't interact with light or with itself except through gravity, felt nothing. It was completely unaffected by the electromagnetic forces that caused the gas to collide and slow down. It just kept going, guided only by its own gravity. This observation was a monumental confirmation. It demonstrated that dark matter is not only real, but it is fundamentally different from the ordinary matter we know. It is collisionless and non-baryonic, a substance that neither emits nor absorbs light and barely even notices when it passes through itself. The bullet cluster provided a clear, almost intuitive snapshot. Here is the visible stuff, and way over here, completely separate, is the invisible stuff that holds the real gravitational power. It was no longer just a theory, it was a picture, and it changed everything. So if dark matter isn't made of the same stuff as you and me, and it clearly doesn't interact with light or even with itself in any significant way, what in the universe could it actually be? This is where the search moves from the cosmic scale down to the subatomic, from mapping invisible halos around galaxies to hunting for individual particles. We know dark matter must be some kind of particle. That's the only framework that fits all the evidence. But pinning down its identity has become one of the greatest and most frustrating challenges in all of physics. For decades, the leading candidate has been a class of particles known as WIMP, or weakly interacting massive particles. The name itself is a perfect description of their proposed nature. They would be massive, meaning they have a significant heft, perhaps anywhere from tens to thousands of times heavier than a proton. And they would be weakly interacting, meaning they barely talk to normal matter, only doing so through the weak nuclear force and gravity. This would make them incredibly difficult to detect, but not impossible. The elegance of the WIMP hypothesis is what captivated physicists for so long. A concept from particle physics called supersymmetry theoretically predicts a perfect candidate, a stable, heavy particle that would have been created in abundance during the Big Bang. The predicted relic density of these particles left over from the early universe matches almost perfectly with the amount of dark matter we observe cosmologically. It was a beautiful, compelling coincidence that felt too good to be wrong. This led to a monumental global effort to find them, deep underground, in abandoned mines and tunnels shielded from cosmic rays. Incredibly sensitive experiments like LUX, Xenon, and Panda X have been waiting for that 1 in a trillion event, the infinitesimal recoil of an atomic nucleus caused by a WIMP passing through it. These detectors are marvels of engineering, filled with ultra-pure liquid xenon and surrounded by layers of shielding to block out any background noise. They have become exponentially more sensitive over the years, yet after decades of searching, they have found nothing, not a single confirmed signal. The parameter space where WIMP were expected to live has been systematically ruled out, forcing physicists to confront an uncomfortable possibility. Their favorite candidate might simply not exist. This failure has opened the door for other, more exotic ideas. One particularly intriguing candidate is the axion, originally proposed to solve a completely different problem in particle physics involving the symmetry of the strong nuclear force. Axions are the antithesis of WIMP. They would be incredibly light, potentially billions of times lighter than an electron, and would behave less like discrete particles and more like a pervasive, sloshing cosmic field. Because of their wave-like nature, vast numbers of them would be needed to account for the dark matter, meaning they would be everywhere. The strategy for detecting them is just as strange. Powerful magnetic fields are used to try and convert these ghostly particles into faint microwave photons, which ultra-sensitive radio receivers could then hopefully pick up. Experiments like ADMCs are conducting this delicate search, listening for the faint whisper of an action in a universe full of noise. Other theorists look to the neutrino, a known particle that is already elusive and poorly understood, and wonder if a heavier, even more aloof cousin could be the answer. This hypothetical sterile neutrino would interact only through gravity, making it the ultimate ghost particle. It wouldn't even interact through the weak force, making it far more difficult to detect than a standard neutrino. Its existence, however, might explain other astronomical puzzles, like certain mysterious X-ray emissions from galaxies. The list of candidates goes on, from primordial black holes formed in the first instance after the Big Bang to entirely new states of matter we haven't even conceived of yet. Each possibility comes with its own wild implications for the nature of reality and requires a new, ingenious method of detection. The hunt for the dark matter particle is a story of scientific humility. It's a reminder that the universe is under no obligation to conform to our most elegant theories. As we methodically close doors on one idea after another, we are not failing. We are narrowing the path toward a truth that is undoubtedly stranger and more wonderful than we ever imagined. This brings us to the heart of a modern scientific epic, a story of immense patience and ingenuity in the face of one of nature's most stubborn secrets, the direct detection of a dark matter particle. It is a quest that has driven us to build some of the most sensitive machines in history, in some of the most isolated environments on Earth, all for the chance to witness an event so rare it borders on the miraculous. After all, if trillions of these particles are streaming through your body every second without you ever noticing, how do you possibly catch one? The strategy is as bold as the challenge is immense. To have any hope of seeing the faintest whisper of an interaction, scientists must first escape the cacophony of our everyday world. Cosmic rays from deep space constantly bombard Earth's atmosphere, creating a shower of particles that would completely drown out the delicate signal of a dark matter collision. The solution: go deep, miles deep. Laboratories have been established in abandoned gold mines, under mountains, and deep within tunnels, where thousands of feet of solid rock act as a colossal shield, absorbing the cosmic noise and creating a near-perfect silence. In these subterranean cathedrals of science, like the Sanford Underground Research Facility in South Dakota or the Laboratorio Nazionale del Gran Sasso in Italy, the real hunt begins. Inside these silent halls, the detectors themselves are masterpieces of isolation and precision. The leading technology uses enormous vats of ultra-pure liquefied noble gases like xenon or argon, cooled to extraordinarily low temperatures. The concept is to wait for the unimaginably rare moment when a dark matter particle, on its endless journey through the cosmos, actually bumps into the nucleus of an atom in this liquid. This bump or recoil would be infinitesimally small, but it would produce two telltale signatures: an immediate flash of light called scintillation, and a later release of electrons which are drawn upward by an electric field to create a second flash of light. By measuring the timing and ratio of these two light signals, scientists can, in theory, distinguish a potential dark matter interaction from the remaining background radiation that even mountains can't stop entirely. For decades, the workhorse of this search has been the WIMP, the weakly interacting massive particle, and experiments like LUX, XENO-NNT, and Panda-X have been at the forefront. Their approach has been one of relentless scaling and purification. Each new generation of detector is larger, containing more target material to increase the chance of a collision, and more exquisitely clean to reduce any internal background noise. Their progress has been nothing short of heroic, improving their sensitivity by orders of magnitude over the years. Yet the result has been a profound and growing silence. They have not found a definitive signal. Instead, they have meticulously carved away vast territories on the map of possible WIMP properties, ruling out what dark matter is not. Each new, more sensitive result that comes up empty is simultaneously a disappointment and a major step forward, closing doors and forcing physicists to broaden their thinking. This lack of a discovery has spurred incredible innovation, pushing the search in new and even more exotic directions. If the heavy WIMP remain elusive, perhaps the answer lies with much lighter particles like axions. Detecting an axion requires a completely different philosophy. Instead of waiting for a nuclear recoil, experiments like the Axion Dark Matter experiment or ADMX use a powerful superconducting magnet to create a strong magnetic field. The theory is that within this field, an axion could convert into a very faint microwave photon. The experiment is essentially a giant, ultra-sensitive radio receiver tunable to different frequencies, slowly scanning the dial of the universe, listening for the faint hum of an axion field resonating at one specific station. It's a painstaking process, a world away from the vats of liquid xenon, but it represents the creative diversity now driving the field. Other novel approaches are emerging from the shadows. Some scientists are using ancient minerals deep within the Earth's crust as paleodetectors, looking for damage trails left by dark matter collisions over geological timescales. Others are networking quantum sensors to create a global array that could detect the subtle tidal effects of a passing dark matter stream. The very definition of a detector is being reimagined because the decades-long silence from the traditional experiments is the most important result of all. It tells us that dark matter is even more ghostly, more alien, and more weakly interacting than our most popular theories predicted. We are being guided by absence, by the negative data that is slowly painting a portrait of a particle that may forever lie just beyond the edge of our perception, challenging not just our technology, but the very limits of human ingenuity. But if catching a single dark matter particle directly seems like finding a needle in a cosmic haystack, what if we could instead look for the haystack itself catching fire? This is the fascinating premise behind indirect detection, a completely different strategy that shifts the hunt from the quiet of underground labs to the vastness of space itself. Instead of waiting for a particle to bump into our detector, astronomers are now scanning the skies for the dramatic, high-energy aftermath of dark matter particles meeting their end. The idea is that if dark matter is its own antiparticle, or if two dark matter particles can collide, they might annihilate each other in a spectacular burst of energy, transforming their mass into a shower of secondary particles we can see. Or if a dark matter particle decays after an immensely long lifetime, it might leave behind a specific, faint signature across the cosmos. We're not looking for the ghost itself. We're searching for its shadow, its echo, the telltale splash it makes in the pond of the observable universe. One of the most promising ways to look for this splash is by hunting for gamma rays, the most energetic form of light in the universe. The theory is compelling. When two WIMP or other dark matter particles annihilate, the energy released should produce a cascade of standard model particles, which then quickly decay into a predictable spectrum of gamma-ray photons. Telescopes like the Fermi Gamma Ray Space Telescope have spent years meticulously mapping the entire sky in gamma rays, creating a detailed catalog of sources like pulsars, active galaxies, and other known astrophysical objects. The real trick is to look for an unexplained, diffuse glow of gamma rays that can't be attributed to any of these known sources. Scientists focus on regions where dark matter is predicted to be most densely packed, such as the centers of galaxies like our own Milky Way, or within small, ancient dwarf galaxies that orbit our own. These dwarf galaxies are considered pristine laboratories because they are rich in dark matter, but contain very few of the conventional astrophysical processes that could create gamma rays and muddy the signal. While there have been a few tantalizing hints of an excess of gamma rays from the galactic center, the signal remains controversial and could still be explained by a population of unseen pulsars or other celestial objects. The hunt is a meticulous process of subtraction, patiently removing all the known contributors to see if a dark matter signal remains. Beyond gamma rays, scientists are also turning to another ghostly cosmic messenger, the neutrino. These nearly massless particles barely interact with anything, allowing them to travel in straight lines across the universe from their source without being deflected by magnetic fields. A massive neutrino telescope, like the Ice Cube Observatory buried deep in the Antarctic ice, acts as a giant trap. It uses thousands of sensitive optical sensors to detect the faint flashes of blue light produced on the extremely rare occasion that a neutrino interacts with the ice. If dark matter particles were to accumulate and annihilate in dense regions like the core of the Sun or the Earth, the resulting cascade of standard particles would produce neutrinos that could stream out into space. IceCube is constantly monitoring the Sun and the galactic center, searching for an anomalous directional neutrino flux that could be the signature of dark matter annihilating at its core. It's a long shot, but the clarity of a neutrino signal, if found, would be incredibly difficult to explain away with conventional astrophysics. Finally, there's the search through cosmic rays. These are high-energy particles, mostly protons and atomic nuclei, that constantly rain down on Earth. Sophisticated instruments like the Alpha Magnetic Spectrometer on the International Space Station are meticulously measuring the composition and energy of these particles. The goal is to find an anomalous abundance of certain antimatter particles, like positrons or antiprotons, that could be the fallout from dark matter annihilations happening throughout our galaxy. While an excess of positrons has indeed been found, the challenge once again is attribution. Pulsars are also known to accelerate particles and produce positrons, making it difficult to declare a definitive dark matter discovery. The indirect search is therefore a masterclass in forensic astronomy. It requires an immense understanding of all the messy, complicated astrophysics happening in our galaxy, so we can recognize a signal that truly doesn't belong. It might just be in this cosmic noise, this background static of the universe, that the first undeniable proof of dark matter's identity is finally waiting to be heard. Now, if we zoom out from individual galaxies and even from colossal clusters, we arrive at the grandest architecture of all, the cosmic web. This is the final and most magnificent expression of dark matter's gravitational influence, a universe-spanning network of immense filaments, vast empty voids, and dense clusters that forms the backbone of everything we see. To understand how this web came to be, we have to rewind the clock all the way back to the very beginning, to a time when the universe was almost perfectly smooth. Just after the Big Bang, the cosmos was a hot, dense, and remarkably uniform soup of particles and energy. If you could have taken a snapshot, you would have seen only the tiniest of ripples in this primordial plasma. Quantum fluctuations stretched to cosmic sizes by a brief but explosive period of inflation. These infinitesimal wrinkles in the fabric of space-time were the only seeds of structure in an otherwise featureless void. And it was precisely here, within these tiny density variations, that dark matter found its purpose. Because dark matter doesn't interact with light or radiation, it was free to start clumping together immediately through gravity's relentless pull. Ordinary matter, the protons and electrons that would become stars and galaxies, was still trapped. It was locked in a constant fight with the intense radiation pressure of the early universe, which kept it from collapsing. But dark matter, operating in a ghostly parallel world, felt none of that pressure. It could begin its work unseen, its gravity slowly and silently amplifying those initial ripples. Over hundreds of millions of years, slightly denser regions attracted more and more dark matter, growing into vast halos, while less dense regions were left behind, slowly emptying out. This process didn't happen in isolated patches. It unfolded in 3 dimensions across the entire observable universe. Think of it like this. Imagine pouring syrup onto a waffle. The syrup will naturally flow into the lower-lying grid lines, pooling there and leaving the raised squares mostly bare. In the early universe, the dark matter created that underlying waffle-like grid. The slightly denser regions became the future filaments and nodes of the cosmic web, while the less dense regions evolved into the incomprehensibly massive voids. The ordinary matter, the galactic gas and dust, simply followed the path laid out by this invisible scaffolding. Once the universe expanded and cooled enough for radiation to lose its grip, this normal matter flowed into the gravitational wells carved by the dark matter, collapsing to form the very first stars and galaxies, lighting up the web that had been built in the dark. Today, through massive galaxy redshift surveys that map the 3-dimensional positions of millions of galaxies, we can see this web in stunning detail. These maps reveal a universe not of random scatter, but of intricate order, long, delicate tendrils of galaxies connecting massive nodes at the intersections, all surrounding enormous, dark, and nearly empty voids that can span hundreds of millions of light years. This is the cosmic web, the largest structure in existence, and it is a direct fossil record of the initial conditions of the universe and the silent, gravitational hand of dark matter that sculpted it. It shows us that the beautiful galaxies we see are not the main event. They are merely the glittering ornaments hanging on a Christmas tree we cannot see, tracing the shape of something far greater and more mysterious. This brings us to a mystery that strikes at the very heart of our most sophisticated simulations of the cosmos. A puzzle so perplexing it's earned a dramatically honest name, the too big to fail problem. It's a contradiction that emerged when our virtual universes, governed by the precise rules of the lambda CDM model, grew to such a level of detail that they began making very specific predictions about our own cosmic neighborhood. And what they predicted, quite simply, doesn't match what we see out our window. To understand this, we need to look at the smallest galaxies in our local group, the dwarf spheroidal satellites that orbit behemoths like our own Milky Way and the Andromeda Galaxy. These are faint, diffuse collections of stars, often containing only a few thousand times the mass of our Sun. According to our incredibly powerful computer simulations, the dark matter halos that host these tiny galaxies should follow a specific pattern. The most massive dark matter sub-halos, the ones that simulation tells us are the largest and most robust, should be brimming with enough gravity to hold onto a significant amount of gas. This gas should then cool, collapse, and form a wealth of new stars, creating a satellite galaxy that is both massive and bright. In the parlance of finance, these halos are so large and gravitationally powerful that they are too big to fail at the task of galaxy formation. The simulations confidently predict that we should see several of these massive, bright dwarf galaxies orbiting our Milky Way. But when astronomers go looking for them, the reality is strikingly different. The satellites we actually observe around our galaxy are far punier than the simulations say they should be. They are incredibly faint with very few stars, suggesting they are hosted within dark matter halos that are much less massive and much less dense than what the virtual universe created. It's as if the simulation told us to expect a fleet of mighty battleships patrolling our galactic harbor, but when we look, we only find a few scattered, fragile rowboats. The most massive dark matter sub-halos in the simulations appear to be missing their bright galactic counterparts in the real world. Either the halos themselves are less massive than predicted, or for some reason, the process of forming stars within them was incredibly inefficient, leaving them dark and dim. This isn't just a minor coding error, it's a fundamental tension between our best theoretical model and direct observation. So, what could be causing this discrepancy? Astrophysicists have proposed several intriguing solutions. One possibility is that our understanding of how stars form within these small halos is incomplete. Perhaps fierce stellar winds or powerful supernova explosions in the early universe were far more effective at blasting gas out of these small galaxies than we thought, essentially starving them of the fuel needed to make new stars and leaving them faint. This would mean the dark matter halos are indeed there and as massive as predicted, but they're just not very good at building luminous galaxies. Another, more radical idea involves the very nature of dark matter itself. The standard model assumes it is cold, meaning the particles move relatively slowly, which allows it to clump efficiently into small, dense halos. But what if dark matter is slightly warmer? A warm dark matter particle would be lighter and faster, possessing more thermal motion in the early universe. This would suppress the formation of structure on the very smallest scales, preventing those extremely dense, low-mass halos from ever forming in the first place. In a warm dark matter universe, the smallest halos would be fewer in number and less dense, potentially bringing the simulations into much closer alignment with the faint galaxies we actually observe. The too big to fail problem, therefore, isn't just a puzzle about satellite galaxies. It's a potential window into the fundamental properties of the dark matter particle, a clue that its identity might be even stranger than our coldest, simplest models assume. Yet another profound tension between our simulations and reality emerges when we peer directly into the dark hearts of galaxies, both large and small. This mystery is known as the core cusp problem, and it strikes at a key prediction of how cold dark matter should behave on the very smallest scales. According to the incredibly detailed simulations of cosmic structure formation, the invisible halos of dark matter that cradle galaxies should have a very specific internal architecture. The pull of gravity should cause the dark matter to pile up in an extremely dense, sharp peak right at the very center of the halo. This feature is known as a cusp, and in a cold dark matter universe, it should be a universal signature, a steeply rising density gradient that is mathematically described as a cusp, a singular, intense concentration of mass. This prediction makes perfect sense within the model. Cold dark matter particles moving slowly and interacting only through gravity should naturally sink toward the center of their own gravitational well, piling up in a dense, singular peak. For years, this was considered a cornerstone prediction, a telltale fingerprint that our simulations were correctly capturing the physics of dark matter. The challenge, as always, is to go out and actually test this prediction against the real universe. And once again, the universe has presented a confounding answer. When astronomers measure the distribution of mass within dwarf galaxies and even the central regions of some larger galaxies, they consistently find something entirely different. Instead of a sharp, dense cusp, the dark matter appears to be distributed in a constant density core. The density of dark matter rises as you move toward the center, but then it seems to plateau, maintaining a roughly constant density all the way into the very heart of the galaxy. It's the difference between a mountain that comes to a sharp, Matterhorn-like peak and one that has a flat, mesa-like top. The observations are clear. Many galaxies show this flat core, not the steep cusp the theory demands. How do we even measure this? We can't see the dark matter directly, so we have to infer its distribution by watching how stars and gas move within a galaxy. Their orbital speeds are a direct probe of the gravitational field, and by extension, the mass causing that field. In a galaxy with a dense central cusp, stars near the center should be whipping around at tremendously high velocities, pulled by the intense gravity of that concentrated dark matter. But in galaxy after galaxy, the measured velocities of those central stars are far slower than expected. Their leisurely pace tells us the gravitational pull at the center is much weaker than it should be, meaning the dark matter must be spread out into a more homogeneous, fluffy core rather than a singular, dense cusp. This creates a serious problem for the Standard Model. If our foundational understanding of cold dark matter is correct, then these cusps should be everywhere. Their apparent absence suggests that something is wrong, either with our models or with our basic assumptions about dark matter's properties. One compelling line of thinking points the finger not at dark matter itself, but at the complex and violent astrophysics of normal matter that the simulations might be oversimplifying. The leading solution is known as feedback, a catch-all term for the immense energy that stars and black holes pour back into their surroundings. Imagine a galaxy in its early stages, with a nascent cusp of dark matter beginning to form at its center. Then the first generation of massive stars is born. These stars live fast and die young, exploding as supernova in a relentless series of cosmic detonations. These explosions inject a colossal amount of energy into the surrounding gas, heating it and driving powerful winds that can literally push the gas and the gravitational potential it represents out of the central region. This sudden removal of mass from the center slightly weakens the gravitational well. The dark matter, responsive only to gravity, reacts to this change. As the central mass decreases, the dark matter particles expand outward slightly, effectively puffing up the central cusp and transforming it into a gentler, constant density core. It's a form of gravitational back reaction, where the explosive drama of normal matter fundamentally reshapes the invisible dark matter scaffold that holds it all together. This explanation is elegant, but the debate is far from settled. Some galaxies that show these cores are so tiny and faint that it's hard to imagine they ever had enough star formation to power such transformative feedback. This has led to more radical proposals that go right to the heart of the dark matter paradigm. Perhaps dark matter isn't entirely cold. Maybe it has some small, intrinsic ability to interact with itself through a force other than gravity. If dark matter particles could collide or scatter off one another, even very rarely, that interaction could transport heat and energy from the outer parts of the halo inward, effectively smoothing out the dense central cusp into a more uniform core. Or, as with the too big to fail problem, perhaps dark matter is slightly warmer than we think, with its inherent particle motion preventing it from collapsing into such extremely dense configurations in the first place. The core cusp problem remains a wide open frontier, a stark reminder that the smallest scales can often pose the biggest challenges to our understanding of the cosmos. It seems like a straightforward idea: measure the mass of a galaxy and you'll know how its stars should orbit, but the universe, as it so often does, loves to throw us a curveball, literally. When astronomers began meticulously charting the rotation curves of spiral galaxies, expecting to find a simple pattern, they were met with a baffling diversity that defied easy explanation. Here we find one of the most subtle yet profound mysteries of the cosmic dark matter web. Why do galaxies that look almost identical in size and brightness host dark matter halos that behave in completely different ways? Let's picture two spiral galaxies. Through our telescopes, they appear as stunning twin whirlpools of light, each with a brilliant central bulge and graceful, star-filled arms spiraling outward. They contain roughly the same number of stars, the same amount of glowing gas. By all standard visible metrics, they are cosmic siblings. According to our simplest models of galaxy formation, they should also have assembled similar dark matter halos around them. The gravitational pull from these halos should dictate how stars at different distances from the center move. We would expect their rotation curves, the graph that plots the orbital speed of stars against their distance from the galactic center, to be nearly identical. But when scientists measured them, the results were anything but identical. In one galaxy, the rotation curve rose steeply and then remained perfectly flat far out into the halo, the classic signature of a massive, dominating sphere of dark matter that we've come to expect. But in its apparent twin, the curve told a different story. The orbital speeds of the outer stars were significantly slower, plummeting off at the edges. This suggests a dark matter halo that is far less massive, less dense, or perhaps distributed in a radically different way. This is the mystery of the diversity of rotation curves. It's as if two families built identical-looking houses on the same street, but one house was anchored to a massive, deep foundation of solid bedrock, while the other was perched on a shallow, shifting pile of sand. The visible structure is the same, but the unseen support is utterly different. This presents a monumental challenge to our understanding of galaxy evolution. The cold dark matter model is brilliant at explaining the universe on the largest scales, sculpting the cosmic web with stunning accuracy. But on the scale of individual galaxies, it appears that the simple, gravity-only story is incomplete. The dark matter halo and the luminous galaxy within it are not independent entities. They grow together in a complex cosmic dance. The key to this diversity likely lies in the messy, violent, and stochastic history of the normal matter, the baryons. A galaxy's life is not a peaceful one. It is a story of constant upheaval driven by the very stars it creates. Think of a galaxy not as a static painting, but as a dynamic ecosystem. Intense episodes of star formation create generations of massive stars that live fast and die in spectacular supernova explosions. These explosions pump enormous energy back into the galaxy, heating the gas and driving powerful winds that can blow vast reservoirs of star-forming fuel right out of the galaxy entirely. This process, called feedback, doesn't just affect the gas, it can dramatically reshape the dark matter halo itself. Here's how that might work. In a galaxy that experiences an extremely violent and early burst of star formation, these supernova-driven winds are ferocious. They eject a huge amount of mass from the central regions very quickly. Since gravity is a two-way street, the sudden loss of this concentrated baryonic mass causes the gravitational potential well at the center to become shallower. The dark matter, which was piled up in a dense cusp, responds to this change. The particles, feeling the weakened gravitational pull, naturally migrate outward, effectively puffing up the center of the halo and creating a larger, less dense core. The result is a galaxy with a less massive seeming dark matter halo and a rotation curve that drops off. Conversely, a galaxy with a more quiescent, gentle history of star formation might experience much weaker feedback. Less mass is ejected, the central gravitational well remains deep, and the dark matter is able to stay in its primordial, dense, cuspy configuration. This galaxy will show the strong gravitational signature of a massive dark matter halo and a classic flat rotation curve. The random, chaotic nature of these star-forming events, when they happen, how intense they are, could be the primary factor creating the incredible diversity we observe. Two galaxies that started with the same total mass can end up with dramatically different dark matter distributions, simply because one had a more tumultuous youth than the other. This introduces a fascinating new layer of complexity to our models. It suggests that to truly understand dark matter, we must also become experts in the astrophysics of ordinary matter. The complex interplay of gas cooling, star formation, and explosive feedback. The invisible hand of dark matter builds the stage, but the visible actors, the stars, can literally rearrange the furniture. This mystery forces us to move beyond a one-size-fits-all approach to galaxies and to appreciate the unique biography written in the rotation of every stellar disk. A story where chaos and chance play a leading role in shaping the hidden architecture of the universe. But if the chaotic history of normal matter can reshape dark matter halos, what happens when we pull the lens back to the very largest scales and consider the other great unknown dominating our universe? We've been following the gravitational clues of dark matter, this invisible scaffolding that pulls the cosmos together. Yet, for the past several billion years, a far more mysterious force has been doing the exact opposite, relentlessly pushing the universe apart at an accelerating rate. This is dark energy, and its discovery posed a profound question. Are these two dominant forces, one an attractor, the other a repulsor, somehow connected? Could dark matter and dark energy be two sides of the same cosmic coin? On the surface, they couldn't appear more different. Dark matter operates through gravity. Its pull is local, clumpy, and constructive. It gathers into halos, builds galaxies, and weaves the cosmic web. We infer its presence by watching things move toward each other. Dark energy, in stark contrast, appears to be a property of space itself. Its push is global, smooth, and destructive. It works against gravity's pull, driving galaxies apart from one another at an ever-increasing speed, and we infer its presence by watching things move away from each other faster and faster. One is the ultimate architect of structure, the other is the ultimate agent of dilution and emptiness. They seem to be cosmic opposites, locked in a grand tug of war for the fate of the universe. Yet, this very opposition is what makes some theorists wonder if they are, in fact, related. Both are dark, meaning we cannot see them directly, and have only detected them through their gravitational effects on the universe as a whole. Both are utterly dominant, together making up about 95% of the total mass energy content of the cosmos, and both remain complete mysteries in terms of their fundamental nature. This has led to a fascinating and speculative line of inquiry. Perhaps dark matter and dark energy are not two separate substances, but different manifestations of a single, unified dark sector. One of the most compelling ideas in this space is the concept of interacting dark energy. What if the dark energy field, which is causing the expansion of the universe to accelerate, can somehow interact with dark matter particles? In most models, these two entities ignore each other completely, like strangers passing in the night. But if they could talk, if they could exchange energy, the implications would be revolutionary. Imagine a scenario where dark energy slowly decays into dark matter over cosmological time. This would mean the repulsive force driving expansion could gradually be converting itself into the attractive force that builds structure, a cosmic transmutation that would subtly alter the evolution of the universe. Alternatively, what if dark matter decays into dark energy? This would mean the scaffolding of the cosmos is slowly dissipating, fueling the acceleration, and ultimately leading to a future where the cosmic web is torn apart from within. These are not just wild ideas, they are models that cosmologists are actively testing against precise observations of the cosmic microwave background and the large-scale structure of the universe, looking for any tiny deviation from the standard story that could hint at this secret conversation within the dark sector. Other theories go even further, proposing that dark matter and dark energy are not substances at all, but arise from a fundamental flaw in our understanding of gravity on the largest scales. Modified Newtonian dynamics, or MND, was initially proposed to explain galaxy rotation curves without invoking dark matter by tweaking the laws of gravity. While MND has serious difficulties explaining all the evidence, particularly from galaxy clusters and the cosmic web, it inspired a more radical concept. What if a single modification to Einstein's theory of general relativity could account for both the effects we attribute to dark matter and those we credit to dark energy? This would be an incredibly elegant solution, explaining two mysteries with one master stroke. So far, no such theory has successfully passed all observational tests, but the pursuit highlights a deep desire in physics for unity and simplicity. We are naturally drawn to the idea that the two greatest puzzles in cosmology might share a common origin, a single underlying phenomenon that our current models simply haven't yet captured. Whether they are two interacting components of a dark sector or two illusions created by our incomplete grasp of gravity, their potential connection remains one of the most exciting and profound frontiers in science. A mystery that gets to the very heart of what the universe is made of and how it will end. For centuries, our understanding of the cosmos has been guided by a simple, powerful idea. that the force of gravity, as described by Newton and later refined by Einstein, is universal. It works the same way here on Earth as it does in the farthest reaches of space. But what if that assumption is wrong? What if the mysterious motions of galaxies aren't caused by an invisible substance, but because our fundamental law of gravity simply breaks down on the vast scales of interstellar space? This is the radical proposition at the heart of modified Newtonian dynamics, or MUND, a theory that dares to rewrite the rules of physics to do away with dark matter entirely. The story of MUND begins not with a cosmologist but with an Israeli physicist named Mordechai Milgrom. In the early 1980s, Milgrom was deeply troubled by the galaxy rotation problem. He saw the same flat rotation curves as everyone else, but instead of inventing a new, invisible particle to explain them, he asked a more provocative question: what if gravity doesn't behave as we expect when it becomes incredibly weak? In the outer suburbs of a galaxy, far from the central mass, the gravitational acceleration from stars and gas becomes vanishingly small. Milgrom proposed that below a certain critical threshold of acceleration, Newton's famous law of inverse squares stops working. In this low acceleration regime, he suggested, gravity switches to a new behavior following a simple inverse distance law instead. This tiny tweak to the formula has a dramatic effect. It naturally predicts that the orbital speeds of stars in the outer reaches of a galaxy will become constant, perfectly matching the observed flat rotation curves without a single gram of dark matter. It was an astonishingly simple and elegant solution to one of astronomy's biggest puzzles, and for a certain class of objects, MUND works brilliantly. It is remarkably successful at predicting the rotation curves of individual, isolated spiral galaxies with just their visible matter. For many proponents, this is the theory's greatest strength. It explains the data with what they see as a more parsimonious approach, avoiding the need to invoke an entire universe of unseen particles that have so far eluded every attempt at direct detection. MUND isn't just a single idea. It's inspired a family of theories, including more sophisticated relativistic versions like TVS tensor vector scalar gravity, that attempt to incorporate the theory into a framework that can also challenge Einstein's general relativity on cosmological scales. However, for all its successes with individual galaxies, MUND faces a mountain of contradictory evidence when confronted with the rest of the universe. Its failures are, in the eyes of most cosmologists, fatal. The first and perhaps most powerful blow comes from the bullet cluster. Remember, this cosmic collision cleanly separated the bulk of the mass which traveled with the galaxies from the normal matter, which got stuck in the middle. MUND is a theory about how gravity works. It modifies the force law, but it doesn't provide any new kind of substance that can become separated from visible matter. The gravitational lensing map of the bullet cluster shows us clearly that the gravity is not centered on the visible mass. This is impossible for MUND to explain, as its modified force is still tied directly to the location of the stars and gas. The bullet cluster demonstrates that there is a substance that has gravity but doesn't emit light, and that substance can be physically separated from the light-emitting matter. This is precisely the definition of dark matter. The challenges for MUND only grow from there. The intricate pattern of hot and cold spots in the cosmic microwave background, the afterglow of the Big Bang, is a precise reflection of the composition and geometry of the early universe. The standard lambda CDM model, which includes cold dark matter, predicts this pattern with stunning accuracy. To date, no version of MUND or its relatives has been able to reproduce the power spectrum of the CMB without eventually having to add some form of dark matter anyway. Furthermore, MUND has great difficulty explaining the observed properties of the largest structures in the universe, the formation and evolution of the cosmic web. The vast filaments and clusters of galaxies separated by enormous voids proceeds naturally and elegantly in supercomputer simulations that include dark matter. In a MONDIAN universe, however, structure formation should happen far too quickly and violently, resulting in a universe that looks nothing like the one we actually observe. This leaves physics at a fascinating crossroads. We have one theory, dark matter, that is incredibly successful at explaining the universe on large scales, the CMB, the cosmic web, and galaxy clusters, but requires us to accept the existence of a mysterious, undiscovered particle. We have another theory, MUND, that is surprisingly effective on the small scales of individual galaxies, but fails catastrophically on larger cosmological scales. For the vast majority of physicists, the choice is clear. The evidence for dark matter is simply too overwhelming and comes from too many independent lines of inquiry. MUND is seen as a brilliant but ultimately incomplete idea, a clever fix for one problem that creates a dozen more, yet its persistence is not in vain. It serves as a crucial counterpoint, a stringent test that the dark matter paradigm must constantly pass. It forces scientists to sharpen their models and ensures that the case for dark matter is not built on circular reasoning. In the end, the story of MUND is a testament to the scientific process itself, a bold challenge to the status quo that, even in its shortcomings, helps refine our search for a deeper, more complete truth about the fundamental forces that shape our reality. What if the answer to the dark matter puzzle isn't a new, exotic particle at all, but something we already know exists, just from a different chapter of the universe's history? This intriguing possibility takes us back to the very first instance after the Big Bang, to a time of almost unimaginable density and turbulence. In that seething cauldron of energy, could immense gravitational forces have crushed pockets of matter directly into black holes, bypassing the need for a dying star entirely? These hypothetical objects are known as primordial black holes, and for a time they offered a beautifully simple solution. Dark matter might just be an enormous population of these ancient, invisible cosmic fossils. The appeal is immediate. We already know black holes exist. They have mass, they exert gravity, and they are the very definition of dark. They emit no light. A vast swarm of relatively small, planet-sized or asteroid-sized primordial black holes drifting through the galaxy would be virtually impossible to see directly, yet their combined gravitational pull would perfectly explain the effects we attribute to particle-based dark matter. It's an Occam's razor approach, using a known entity to solve a profound mystery. The challenge, of course, is that the standard model of cosmology doesn't naturally create these objects. They would require incredibly specific and somewhat exotic conditions in the early universe, like patches of space with densities 1,000 times greater than the surrounding area. But if such density fluctuations did occur, perhaps due to a phase transition in the evolving cosmos, primordial black holes could have formed in staggering numbers, becoming the universe's first structures and its hidden gravitational backbone. For decades, this hypothesis was incredibly difficult to test. How do you look for a countless number of invisible objects scattered across the galaxy? The answer came from a clever astronomical technique called microlensing. The principle is straightforward. If a primordial black hole passes directly between us and a distant star, its gravity will act like a tiny lens, bending the star's light and causing it to temporarily brighten. By continuously monitoring millions of stars in nearby galaxies like the Large Magellanic Cloud, telescopes could, in theory, catch these fleeting flashes of amplified light and count the number of invisible gravitational lenses drifting through the galactic halo. Early results from these microlensing surveys, however, delivered a series of heavy blows to the idea. They found far fewer of these microlensing events than would be expected if the entire dark matter halo were made of primordial black holes of a certain mass range. Essentially, if dark matter were primarily black holes between the mass of a large asteroid and the planet Jupiter, we would have seen their lensing signatures. These observations severely constrained the theory, ruling out primordial black holes as the dominant form of dark matter across a wide spectrum of possible masses. For many, it seemed the case was closed, but science has a way of resurrecting dismissed ideas with new data. The game-changing moment came in 2015 with the first direct detection of gravitational waves by the LIGO Observatory. The signal was unmistakable: two black holes, each about 30 times the mass of our Sun, spiraling into each other and merging. This was shocking. According to our understanding of stellar evolution, black holes that size shouldn't form from the collapse of a single star. So where did they come from? The possibility that they were primordial black holes, formed in the early universe and wandering through space for billions of years before finally meeting, suddenly seemed far more plausible. If such objects were common, they could account for a significant fraction of the dark matter, existing in a mass window that the earlier microlensing surveys hadn't been sensitive to. This ignited a fierce debate that continues to this day. Proponents point to the growing catalog of unexpected black hole mergers as evidence for a hidden population of ancient black holes. Skeptics, however, highlight other problems. Such a large number of massive black holes would inevitably disrupt other cosmic structures. They would gravitationally rip apart fragile dwarf galaxies. They would subtly alter the precise signals we see in the cosmic microwave background, and they would inject a great deal of energy into the interstellar medium through their interactions. So far, detailed searches for these secondary effects have come up empty, placing stringent new limits on how much of the dark matter budget could realistically be filled by even these larger primordial black holes. The current picture is one of fascinating complexity. It seems increasingly unlikely that a single, monolithic population of primordial black holes of any one size can explain all of dark matter. The constraints from microlensing, stellar dynamics, and the cosmic microwave background have painted them into a very narrow corner. Yet, the possibility remains that they could make up a few percent of it, or that they exist in a wide range of masses we have yet to fully probe. They may not be the sole actor in the dark matter story, but they could still play a crucial supporting role, a hidden cast of ancient gravitational anchors that formed not from the death of stars, but from the violent birth of the universe itself. As the search for the classic heavy WIMP continues to yield empty results, the physics community has increasingly turned its attention to a candidate that is, in almost every way, its complete opposite: the action. This hypothetical particle is a fascinating example of how the solution to one deep puzzle in physics might accidentally provide the answer to another. The story of the action doesn't begin with astronomy or cosmology, but deep within the nucleus of the atom, with a problem concerning the strong nuclear force. Quantum chromodynamics, or QCD, is the brilliant theory that describes how quarks and gluons interact to form protons and neutrons. It is a cornerstone of modern physics, but for all its successes, it had a perplexing flaw. The equations of QCD naturally allow for a certain kind of symmetry violation that would cause the neutron to possess a large electric dipole moment, a sort of internal charge separation that would make it act like a tiny, lopsided compass. This effect has been searched for with incredible precision, and the result is clear: it doesn't exist. The neutron's symmetry is perfectly preserved. To explain why this symmetry is so perfectly observed, physicists Roberto Pexi and Helen Quinn proposed an elegant solution: a new, fundamental symmetry in nature that would naturally cancel out this problematic effect. Shortly thereafter, Frank Wilczek and Steven Weinberg realized that this new symmetry would inevitably predict the existence of a new, very light, very weakly interacting particle. Wilczek named it the action after a brand of laundry detergent because it was theorized to clean up the problem in the strong force. For a long time, the action was considered a curious footnote in particle physics. But as the WIMP searches came up empty, cosmologists realized that this humble particle had all the right properties to be dark matter. Unlike the heavy, discrete WIMP, axions would be billions of times lighter than an electron. Because of their incredibly low mass, they would be produced in staggering numbers in the early universe, behaving less like individual particles and more like a pervasive, coherent field that fills all of space. This field would oscillate at a frequency set by its mass, and these collective oscillations would have the exact right characteristics to naturally account for the cold dark matter we observe gravitationally. The action went from being a solution to a nuclear problem to a prime candidate for the majority of the mass in the universe. Detecting such a ghostly entity, however, requires a radical departure from the massive underground vats used to hunt WIMP. The primary strategy for finding axions is as ingenious as the particle itself, centered on a phenomenon known as the Primakov effect. The theory predicts that in the presence of an extremely powerful magnetic field, an axion could convert into a microwave photon. This is the key. Experiments are essentially designed to be giant, ultra-sensitive radio receivers tuned to listen for this very specific, faint whisper of a conversion. The most prominent of these endeavors is the Axion Dark Matter experiment, or a DMX. Located at the University of Washington, a DMX is a technological marvel. At its heart is a powerful superconducting magnet that creates an intense magnetic field. Inside this field is a resonant cavity, a kind of tuned chamber designed to amplify a microwave signal of one very specific frequency. The concept is to spin the dial on this cavity, slowly adjusting its size to scan through millions of possible frequencies, each corresponding to a different possible mass for the action. It is an exercise in immense patience, a search for a single, faint radio station in a cosmic static of unimaginable size. The detectors are cooled to near absolute zero to eliminate any thermal noise, and they are shielded from all external radio interference, making them some of the quietest listening posts ever built. The challenge is that the predicted frequency of the axion signal is not known. It could be anywhere within a vast range. Scanning through every possibility is a painstakingly slow process that has been underway for years. Recent upgrades have made a DMX and other experiments like it sensitive enough to probe deeply into the most promising ranges of axion mass. While a definitive discovery has not yet been made, the very fact that these experiments are now operational and collecting data marks a monumental shift in the dark matter hunt. We are no longer just looking for heavy particles crashing into nuclei. We are also listening with ever-increasing sensitivity for the faint hum of a cosmic field that may have been ringing since the dawn of time, its oscillations holding the key to the hidden architecture of the cosmos. But what if the answer to these small-scale puzzles lies not in the complexity of normal matter, but in a fundamental revision of dark matter's own nature? For decades, the reigning assumption has been that dark matter is cold, composed of slow-moving, heavy particles that clump together efficiently from the universe's earliest moments. This cold dark matter model, or CDM, is spectacularly successful on the grandest scales, perfectly predicting the cosmic web we observe. Its struggles begin when we zoom in. The too big to fail and core cusp problems suggest that on the scale of individual dwarf galaxies, CDM might be a little too good at making small, dense clumps. This has led a growing number of physicists to consider a compelling alternative. That dark matter isn't cold but warm. The warm dark matter scenario introduces a single, crucial tweak to the particle's properties. Instead of being heavy and slow, a warm dark matter particle would be significantly lighter. This lower mass means that in the searing heat of the early universe, these particles would have been born moving at a significant fraction of the speed of light. They were relativistic. This inherent speed, this thermal motion, is the key that unlocks a different cosmic history. You can think of it like the difference between trying to build a structure out of sand versus building it out of mist. Cold dark matter acts like sand. Its particles move slowly and readily stick together, piling up into countless tiny granules right from the start. Warm dark matter, however, behaves more like a fine mist. Its particles move so quickly that they resist being trapped in very small gravitational wells. They effectively iron out the tiniest wrinkles in the primordial universe. This has a dramatic effect on the very first stages of structure formation. In a warm dark matter cosmos, the smallest dark matter halos, those that would later host the faintest dwarf galaxies, are simply never born. The particle motion prevents it. Structure formation instead begins at a larger floor or minimum size. The first halos to form are larger and less dense than their CDM counterparts. This directly addresses the too big to fail problem. There simply wouldn't be a large population of massive, dense subhalos for the missing dwarf galaxies to inhabit. The satellites that do form would naturally be fewer in number and would reside in puffier, less concentrated halos, which could neatly explain the observed cores in their centers rather than dense cusps. It's an elegant solution that replaces complex astrophysical feedback with a simple, fundamental property of the particle itself. However, this elegance comes with its own set of serious challenges. The most significant constraint comes from the earliest galaxies we can observe. The high thermal motion of warm dark matter particles suppresses the formation of the very first structures, delaying the onset of star and galaxy formation. Astronomers using the James Webb Space Telescope are now peering back to the universe's infancy, finding surprisingly large and mature galaxies at extremely early times. A universe with warm dark matter might have struggled to form these colossal structures so quickly, potentially putting it at odds with these new observations. Furthermore, while warm dark matter solves the problem of too many small structures, we must ensure it still allows for enough small structures to form at the right time to match the population of dwarf galaxies we do see orbiting the Milky Way. It's a delicate balancing act requiring the particle's mass and therefore its free streaming length to be fine-tuned within a very narrow window. The hunt for a viable warm dark matter candidate has centered largely on the sterile neutrino. This hypothetical particle is a heavier, more aloof cousin of the standard neutrino, interacting only through gravity. It would be sterile because it wouldn't even feel the weak nuclear force, making it the ultimate ghost particle. If sterile neutrinos exist with a mass in the right range, a few kilo-electronvolts, they could naturally behave as warm dark matter. Intriguingly, a decay signature from a sterile neutrino could also potentially explain a mysterious, faint X-ray emission line that has been detected from certain galaxies and clusters, though this signal remains controversial and unconfirmed. The debate between cold and warm dark matter is a perfect example of science at a crossroads. Do we double down on the cold paradigm and develop more sophisticated models of galaxy formation to resolve its small-scale tensions? Or do we take the observational hints seriously and explore a warmer, lighter alternative that offers elegant solutions but risks failing other critical tests? This isn't just an academic exercise. The answer holds profound implications for the fundamental properties of the universe's dominant material. The warm dark matter scenario reminds us that we must remain open to all possibilities, ready to follow the evidence even if it leads us to rewrite the basic rules of the cosmic game. Yet after decades of searching the skies for these telltale flashes, the cosmos has responded with a profound and puzzling silence. We have not seen the clear, unambiguous signal of dark matter annihilations that our most promising models predicted. This is the annihilation mystery, a contradiction that forces us to ask whether we are looking for the right thing in the right way, or if the very nature of dark matter is far more elusive than we ever imagined. One compelling explanation for this absence is that our basic assumption about how dark matter is distributed could be overly simplistic. Our models often assume a smooth, predictable density of dark matter in places like the galactic center. But what if the reality is far lumpier? The process of structure formation might leave behind a landscape of dense subhalos and fine-grained clumps within the larger halo. If dark matter annihilates more rapidly in regions of higher density, these ultra-dense clumps would have burned through their fuel much faster in the early universe, effectively depleting the local source of annihilation. What we're left with today could be a much more diffuse and less energetic population, resulting in a faint signal that gets lost in the astrophysical background noise. It's like expecting to find a roaring bonfire in a forest, but because the kindling was so dry, it burned intensely and quickly billions of years ago, leaving behind only scattered, cooled embers that are difficult to spot. Perhaps the answer lies not in the distribution, but in the fundamental physics of the particle itself. The entire WIMP paradigm is built on a concept known as the WIMP miracle, the beautiful coincidence that a particle interacting through the weak force would naturally freeze out of the early universe in exactly the right abundance to be dark matter. This miracle, however, relies on a specific and efficient process of annihilation. What if dark matter particles are their own antimatter counterparts, a property known as being a Majorana particle? While this would allow for annihilation, the specific channels through which they annihilate could produce particles we aren't optimally tuned to detect, like neutrinos, instead of the gamma rays we've been focusing on. Or the cross-section, the probability that two particles will actually annihilate upon meeting, could be much, much smaller than the weak scale value we assumed. Dark matter might be so incredibly reluctant to interact, even with itself, that these events are exponentially rarer than our telescopes are sensitive to. This leads us to the most radical possibility of all, that dark matter simply doesn't annihilate. The search for these signals is fundamentally tied to the idea that dark matter is a thermal relic, a particle that was once in thermal equilibrium with the hot plasma of the Big Bang. But what if it never was? If dark matter was produced through a non-thermal mechanism, like oscillations of a primordial field or as a consequence of the universe's expansion, it may never have required efficient annihilation to reach its current abundance. In such models, the particles would have no reason to annihilate with each other today. We would be patiently listening for an echo that was never uttered, searching for a signal that fundamentally does not exist. This realization is guiding physicists to broaden the hunt, to design new searches that are sensitive to fainter and more exotic signatures, and to remain open to the possibility that the universe's greatest component is content to remain in the shadows, its secrets guarded by its profound and absolute silence. So if dark matter is content to simply pass through itself without a second glance, why would we ever think it could do anything else? The standard model assumes exactly that dark matter is collisionless, feeling only the pull of gravity. But what if that's not the full story? What if, on very rare occasions, these ghostly particles actually bump into one another? This is the intriguing premise behind self-interacting dark matter, a hypothesis that dares to suggest dark matter might have a tiny social life after all. Imagine two galaxies passing through each other, their stars and dark matter halos overlapping. In the standard view, the dark matter from each galaxy would simply coast right through the other, completely unaffected. But if dark matter particles could interact with each other through some new, unknown force, a dark force, the story changes. During a close encounter, these particles could actually scatter off one another, much like billiard balls on a cosmic pool table. This interaction wouldn't be strong or frequent, but even a slight possibility changes everything about how dark matter behaves within the dense environments of galaxies and clusters. It introduces a form of friction, a way to transport energy and momentum within the halo itself. This idea isn't just a theoretical curiosity. It was born from a need to solve those persistent small-scale puzzles we've encountered, particularly the core cusp problem. Recall that simulations predict a sharp, dense peak of dark matter at the centers of galaxies, but observations consistently find a soft, constant density core. Self-interacting dark matter offers an elegant mechanical solution. In a crowded galactic center, dark matter particles would have more opportunities to collide. These collisions would effectively transport heat from the hotter, outer parts of the halo inward toward the cooler center. This influx of energy would cause the central particles to move outward, slightly puffing up the core and smoothing out that dense cusp into a gentler, plateau-like distribution. It's a self-regulating process, using the dark matter's own rare interactions to explain why galaxy centers aren't as sharply concentrated as our simplest models suggest. The beauty of this model is its flexibility. The strength of the interaction is defined by a cross-section, essentially the probability that two particles will collide. This can be tuned to match observations. A cross-section that is too large would make dark matter behave almost like a fluid, smearing out structure formation far too much. But a cross-section that is just right, roughly on the scale of a proton, which is enormous by particle physics standards but incredibly tiny on astronomical scales, can perfectly alleviate the tensions in dwarf and low surface brightness galaxies while leaving the successful large-scale predictions of the cold dark matter model completely intact. The cosmic web, the cluster collisions, the overall abundance of structure, all of that remains beautifully preserved. Of course, introducing a new force of nature is a serious proposition, and it must pass rigorous tests. The most famous of these is, once again, the bullet cluster. This cosmic collision was a brilliant test for collisionless dark matter because it showed the mass the dark matter sailing ahead of the gas. For self-interacting dark matter, this observation is not a problem but a key constraint. The interaction cross-section must be small enough that during a fast, high-energy event like the bullet cluster collision, the dark matter particles still don't have enough time to collide significantly. They still behave largely as if they are collisionless, which is exactly what the lensing map showed. The model elegantly explains why dark matter acts one way in the slow, dense environments of galaxy cores and another way in the violent, high-speed realm of cluster collisions. The search for evidence of these interactions is now a major frontier. Astronomers are meticulously studying the shapes of dark matter halos in countless galaxies, looking for telltale signs of particle scattering. They are also investigating even more exotic possibilities, like the idea that these self-interactions could lead to the formation of a dark disk within our own Milky Way, a hidden mirror of our familiar stellar disk, or that they could allow dark matter to cool and collapse to form dark stars or even dark black holes. The self-interacting dark matter hypothesis transforms dark matter from a simple, passive anchor into a dynamic substance with its own rich internal physics, opening a door to a hidden sector of the universe that might be far more complex and fascinating than we ever dreamed. Now, let's shift our focus from the smallest galaxies to the very largest structures in the universe, the colossal galaxy clusters. These are the metropolises of the cosmos, containing hundreds or even thousands of individual galaxies, all bound together by gravity and embedded within a superheated plasma that glows in X-rays. And at the heart of these immense structures lies another compelling dark matter mystery, one that reveals a complex and sometimes contradictory relationship between what we see and what we can only weigh. When we use the powerful tool of gravitational lensing to map the dark matter in these clusters, we don't always find a simple, smooth halo. Instead, we discover a landscape of puzzling peaks and valleys, a distribution that doesn't always neatly match the locations of the galaxies or the hot gas, forcing us to question our most basic assumptions about how dark matter behaves in the most massive and dynamic environments. The primary method for uncovering this hidden mass is, as we've discussed, gravitational lensing. The immense gravity of a galaxy cluster warps the fabric of spacetime around it, acting as a giant natural telescope. This lens distorts the images of background galaxies, stretching them into faint, telltale arcs. By meticulously measuring the precise shape and degree of this distortion across the entire cluster, a technique called weak lensing, astronomers can create a detailed map of the total mass distribution. It's like taking an X-ray of the cluster's gravitational skeleton. The results are often stunning, revealing a massive, smooth halo of dark matter that cradles the entire cluster. But sometimes the picture is far more complicated. In clusters that are the product of recent, violent collisions, like the famous bullet cluster, these lensing maps show the dark matter is clearly separated from the visible matter. This makes perfect sense for collisionless dark matter. But what about clusters that are relaxed, that have settled into a stable, seemingly peaceful state after billions of years? Here, our models predict the dark matter should have settled into a smooth, symmetric, and predictable distribution, neatly centered on the cluster's brightest galaxy and the peak of the X-ray gas. Yet, in many cases, it hasn't. This is where the mystery deepens. Astronomers have found several massive, relaxed clusters where the center of the dark matter map, as revealed by lensing, is subtly but definitively offset from the center of the hot gas, and sometimes even from the central galaxy itself. This is profoundly strange. After so much time, gravity should have pulled every component, stars, gas, and dark matter, into a harmonious, co-located equilibrium. Finding them out of sync is like seeing a perfectly still pond where a pebble was dropped not in the center, but slightly off to the side. It suggests something is preventing the water from settling. What could possibly be powerful enough to push around the dominant form of matter in the universe, to prevent it from reaching a state of rest? One leading hypothesis points back to the dramatic astrophysics of the normal matter. The superheated gas at the cluster's core is a cauldron of violent activity. The central supermassive black hole, often billions of times the mass of our Sun, can erupt in cycles of unimaginable energy. As it devours material, it blasts out colossal jets of plasma and radiation, effectively heating the surrounding gas and pushing it around. This creates powerful pressure waves that ripple through the cluster's core. The idea is that these waves could actually interact with the dark matter gravitational potential. If the dark matter is not entirely cold and collisionless, but has even a tiny ability to interact with itself, this energetic feedback from the black hole could give it enough of a nudge to shift its center slightly away from the gas. It would be a tiny effect, but over millions of years, it could be enough to create the observable offsets. Another possibility is that these apparently relaxed clusters aren't as peaceful as they seem. They might be the products of a recent minor merger, a smaller group of galaxies plowing into the main cluster at a certain angle. The visible galaxies and gas from this merger would have quickly mixed in, but the dark matter, which doesn't experience friction, could be oscillating or sloshing around the cluster's center like a slow-motion wave, taking much longer to settle down. We might be catching these clusters at a very specific time in this long settling process, witnessing a temporary misalignment that will eventually correct itself over billions of years. Each of these explanations challenges our understanding. The black hole feedback scenario suggests a more complex dialogue between dark and normal matter than we thought possible. The sloshing scenario implies that the timescales for dark matter to reach equilibrium are far longer than our simulations predict, hinting at properties we haven't yet accounted for. Every detailed map of a galaxy cluster's dark matter is more than just a picture. It's a profound stress test for our entire cosmological model, revealing subtle cracks and tensions that point toward a richer, more dynamic truth about the invisible universe. But to truly test this idea, we need a time machine, a way to peer back across billions of years and measure dark matter's gravitational influence on the ancient universe. Incredibly, astronomy provides us with exactly that. The light from the most distant quasars and galaxies has been traveling for so long that it serves as a fossil record of cosmic conditions in the distant past. By analyzing this ancient light, we can weigh galaxies from different cosmic eras and see if their dark matter halos behaved the same way then as they do now. Some of the earliest studies did just that, looking at the rotation speeds of gas in massive, star-forming galaxies when the universe was only a quarter of its current age. The results were startling. These primordial galaxies appeared to be completely dominated by their normal matter. The gravity from their gas and stars seemed sufficient to explain their rotation, with little room left for a significant dark matter halo. This was in stark contrast to modern galaxies, which are overwhelmingly dominated by their dark matter. If confirmed, this would be revolutionary, suggesting that dark matter's role was somehow weaker or different in the early cosmos. However, the universe is rarely so straightforward. Later observations with more advanced telescopes, including the revolutionary James Webb Space Telescope, have begun to paint a more complex and nuanced picture. While some of those early, massive galaxies might indeed have had unusual properties, a broader survey reveals that dark matter's gravitational signature is indeed present in the ancient universe, even if it manifests differently. The key lies in the turbulent lives of these early galaxies. The universe was a far more violent place 10 billion years ago, crowded with rich reservoirs of gas and bustling with frantic star formation. In such an environment, the powerful forces of feedback, the intense radiation and supernova explosions from massive young stars, could have easily overwhelmed the gentler pull of gravity, effectively pushing the normal matter around and temporarily masking the underlying gravitational potential of the dark matter halo. It wouldn't be that the dark matter wasn't there. It would be that the normal matter wasn't yet settled neatly into its gravitational cradle, making it incredibly difficult for us to get a clean measurement from our vantage point in the future. The most tantalizing possibility, however, remains that of a genuine time variation in dark matter's fundamental properties. Could the particle itself evolve? This idea ventures far beyond the standard model and into some of the most speculative realms of theoretical physics. One hypothesis suggests that dark matter might be linked to a dynamic field that permeates space, similar to the proposed quintessence fields for dark energy. If this field has changed its value over the lifetime of the cosmos, it could subtly alter the mass or interaction strength of dark matter particles, leading to a gravitational influence that slowly weakens or strengthens over billions of years. Another, even more exotic concept is that dark matter particles could be inherently unstable, slowly decaying into other, lighter particles over cosmological timescales. If this decay were ongoing, the total amount of dark matter in the universe would be gradually decreasing, its gravitational grip on galaxies slowly loosening epoch by epoch. While there is no definitive evidence for this yet, it offers a breathtakingly dynamic view of the cosmos, where the very rules of the game are not fixed but are changing in a slow, cosmic dance that we are only beginning to learn how to measure. This gravitational conversation between the invisible and the inescapable leads us to one of the most fascinating and speculative frontiers in astrophysics: the mysterious relationship between dark matter and black holes. It's a cosmic partnership built on gravity alone, where the universe's most enigmatic phenomenon meets its most extreme environment. We've long thought of black holes as the ultimate endpoints of gravity, but what if they are also powerful tools, natural laboratories that can amplify and reveal the subtle presence of the dark matter that surrounds them? The connection begins with accumulation. Imagine a supermassive black hole sitting at the heart of a galaxy, a gravitational titan millions of times the mass of our Sun. Its immense pull acts like a cosmic vacuum cleaner, relentlessly drawing in everything nearby. Stars, gas clouds, and crucially, dark matter particles are all pulled inward. But while ordinary matter can collide, heat up, and radiate away energy, allowing it to spiral inward in a bright, chaotic accretion disk, dark matter behaves differently. Because it doesn't emit light or experience electromagnetic friction, a dark matter particle on a trajectory toward the black hole won't slow down easily. It can whip around the black hole on a highly elongated orbit, only to swing back out into the halo. Over countless orbits, however, even these ghostly particles can lose a tiny amount of energy through gravitational radiation, a process that slowly tightens their path. This could lead to the formation of an incredibly dense, invisible cloud of dark matter, a spike, crowding the space immediately around the black hole's event horizon. The density in this spike could become astronomically high, orders of magnitude greater than in the surrounding halo, turning the black hole's immediate vicinity into a concentrated reservoir of dark matter. This dense concentration could have a direct and measurable impact on the black hole itself, potentially influencing its growth and evolution. If dark matter can indeed be captured and consumed, it would provide a steady, low-key source of mass accretion alongside the more dramatic feasts of gas and stars. For isolated black holes in regions with little gas, this dark matter fuel could be the primary mechanism for very slow, steady growth over billions of years. Furthermore, the gravitational influence of this dense dark matter spike would alter the very fabric of spacetime around the black hole in a unique way. It could subtly change the orbital dynamics of stars and gas that venture close, and it would definitely affect how the black hole merges with others. The presence of a massive dark matter spike adds an extra layer of gravitational complexity to these events, a signature that might be etched into the most energetic phenomena in the universe. This brings us to the most promising way to detect this hidden relationship: gravitational waves. When two black holes spiral toward each other and finally merge, they shake the fabric of spacetime itself, sending out ripples that we can now detect with observatories like LIGO and Virgo. The properties of these waves, their frequency, amplitude, and how they change over time, are a precise record of the merger, encoding the masses and spins of the black holes involved. But if this merger happens within a dense cloud of dark matter, the story changes. The gravitational pull of the dark matter spike exerts an additional drag on the orbiting black holes, like trying to run through water instead of air. This dynamic friction would alter the in-spiral process, causing it to proceed faster or slower than it would in a vacuum, and potentially leaving a distinct imprint on the gravitational wave signal. As the black holes finally merge, the violent event could disturb and even scatter the dark matter spike, releasing a burst of gravitational radiation that carries its own unique fingerprint. The next generation of gravitational wave detectors, with their vastly improved sensitivity, will be listening intently for these subtle deviations from the predictions of pure general relativity. A single anomalous signal from a black hole merger could be the first direct evidence not just of a dark matter spike, but of dark matter's particle nature itself, revealing how it behaves in the most extreme gravitational field imaginable. Yet, this elegant picture is fraught with its own complexities and uncertainties. The very existence of these ultra-dense spikes is a subject of intense debate. The chaotic environment around a supermassive black hole is not static. It's shaped by a violent history of mergers and the infall of massive objects. A close encounter with a star cluster or another black hole could easily disrupt and wipe out a nascent dark matter spike long before it reaches its theoretical density. The final word on this mysterious connection will likely come from a combination of precision astronomy, carefully mapping the motions of stars near galactic centers to infer the detailed mass distribution, and the growing science of gravitational wave astronomy. Each new merger detected is another data point, another opportunity to see if the silent, unseen partner in the cosmic dance has left its mark on the music of the spheres. But to truly understand the constraints that bind our theories, we must return to the oldest light we can see: the cosmic microwave background. This faint, cold glow is the cooled remnant of the Big Bang's fiery dawn, a snapshot of the universe when it was a mere 380,000 years old. At that moment, the expanding cosmos had cooled just enough for protons and electrons to combine into neutral hydrogen atoms, a pivotal event called recombination. This allowed photons, which had been constantly scattering off free electrons, to finally travel freely across space. These are the photons we detect today as the CMB, and they carry with them an imprint of the universe's infant structure, a treasure trove of information encoded in tiny temperature differences anisotropies across the sky. It is within this intricate pattern of hot and cold spots that dark matter's signature is irrevocably etched, providing our single most powerful set of constraints on its fundamental nature. The reason the CMB is such a powerful probe is that it captures the universe at a time when gravity and radiation were locked in a delicate tug of war. The entire cosmos was filled with a plasma of photons, electrons, and atomic nuclei, all seething together, and woven throughout this plasma was the dark matter. But unlike the ordinary matter, dark matter was immune to the intense radiation pressure. Photons simply passed right through it. This meant that while ordinary matter was being buffeted and smoothed by light, preventing it from collapsing, the dark matter was free to respond to gravity's pull alone. It could begin clumping together immediately, silently building the gravitational wells that would later trap the ordinary matter once the radiation pressure eased. The tiny density fluctuations in the dark matter were the seeds from which all future structure would grow, and the photons of the CMB bear witness to their size and distribution. When we look at the detailed power spectrum of the CMB, the graph that shows the strength of temperature fluctuations at different angular scales, we are essentially reading a detailed report on the contents of the early universe. The positions and heights of the peaks in this spectrum are exquisitely sensitive to the amounts of dark matter, ordinary matter, and dark energy, as well as the geometry of the universe itself. The first peak, for instance, tells us the universe is geometrically flat, a finding that requires a specific total density of matter and energy. The ratios of the subsequent peaks are a direct measure of the balance between ordinary matter and dark matter. This is because the ordinary matter, coupled to the radiation, experienced acoustic oscillations. It was sloshing back and forth in the dark matter gravitational wells, creating a predictable pattern of compressed hotter and rarefied colder regions. The dark matter, sitting motionless at the bottom of these wells, governed the depth and scale of these oscillations. The precision of this measurement is staggering. Data from space missions like Planck have allowed cosmologists to determine that dark matter makes up about 26.8% of the universe's total mass energy budget, while ordinary matter constitutes a mere 4.9%. This 5-to-1 ratio is now a cornerstone of modern cosmology, but the constraints go far deeper than just a simple abundance measurement. The CMB also places incredibly tight limits on how dark matter could have interacted with itself and with ordinary matter in those first moments. If dark matter had any significant interaction with photons, if it could scatter light, even very weakly, it would have left a smearing effect on the finest details of the CMB patterns. We see no such smearing. This tells us dark matter must be electromagnetically neutral to an incredible degree. It is profoundly dark. Furthermore, if dark matter particles had a significant ability to interact with each other through some unknown force, a property known as self-interaction, this would have suppressed the formation of the smallest clumps in the early universe. This would, in turn, alter the pattern of the CMB fluctuations on very small angular scales. The Planck data show no evidence for this suppression, effectively ruling out large self-interacting cross-sections and forcing models like SIDM to operate with only very weak interactions. The CMB even constrains the velocity of dark matter particles. If they were moving too fast in the early universe, a characteristic of warm, dark matter, they would have washed out small-scale structure, again leaving a telltale sign in the CMB power spectrum. The fact that we don't see this strongly favors the cold dark matter model, where particles were moving slowly enough to clump efficiently from the very start. In essence, the cosmic microwave background acts as a universal referee. Any proposed model of dark matter, from WIMP to axions to sterile neutrinos, must first and foremost be able to reproduce the exquisitely detailed pattern of the CMB. It is not enough for a theory to explain galaxy rotations or cluster collisions. it must also account for the precise conditions of the universe at 380,000 years old. This ancient light is our most reliable witness, and its testimony has already ruled out entire classes of possibilities, sharply guiding the hunt toward a particle that is cold, collisionless, and utterly silent in its interactions with light, a ghost whose shadow is cast across the very beginning of time. If our own Milky Way seems like a dark matter mystery, the tiny, faint dwarf galaxies that orbit it are an even deeper enigma. These are the most dark matter-dominated objects we know of in the entire universe, yet their very existence and internal structure are creating some of the most serious headaches for cosmologists. They are the purest laboratories we have for studying dark matter's behavior, precisely because they contain so little of the messy astrophysics of normal matter. But instead of providing simple answers, these cosmic minnows are shouting complex questions. A dwarf spheroidal galaxy is a ghostly sight. It might contain only a few thousand stars, a minuscule fraction of the hundreds of billions in a galaxy like our own. They are so diffuse that if you were standing on a planet in one, the night sky would be nearly black, with just a handful of faint, distant suns punctuating the darkness. Yet, despite this lack of visible stuff, the motions of those few stars tell an incredible story. They are whipping around at speeds that should instantly fling them out into the void. The only thing holding them together is the immense gravitational pull of a truly colossal dark matter halo. In some of these dwarfs, dark matter outweighs normal matter by a factor of 1,000 to 1. They are not galaxies with dark matter, they are dark matter halos that, almost as an afterthought, manage to collect a sprinkling of stars. This incredible dominance makes them the perfect place to test our theories. With so few stars, there's very little of the complex supernova feedback or black hole activity that can reshape dark matter distributions in larger galaxies. What we see in a dwarf should be a pristine reflection of dark matter's innate properties, a clean signal from the hidden majority of the cosmos. But when we look, the signal is confusing. The first major puzzle is their sheer abundance or lack thereof. Our most sophisticated supercomputer simulations of a cold dark matter universe predict that our Milky Way should be surrounded by a swarm of hundreds, even thousands, of these small dark matter clumps. But we only see a few dozen dwarf galaxies. This is the missing satellites problem. Where are all the rest? Have most of them failed to form stars, leaving their dark matter halos completely invisible? Or is there something fundamentally wrong with the simulation's prediction? The second, and perhaps more profound, puzzle is what's happening in their cores. As we discussed earlier with the core cusp problem, the simulations predict that the dark matter density should rise sharply toward the center of these dwarf halos, creating a steep, dense peak. But when astronomers measure the motions of stars in these faint galaxies, the story is different. The stars move too slowly in the central regions, indicating that the dark matter is not piled up in a sharp cusp, but is instead distributed in a much flatter, constant density core. It's like finding a mountain that, instead of coming to a peak, has a flat plateau at its summit. This is a direct challenge to the cold, collisionless dark matter model. If dark matter is just simple, passive particles that only feel gravity, why doesn't it collapse into the dense cusps the simulations so confidently create? These twin puzzles have forced physicists to consider some radical solutions. One compelling idea brings the story back to the very beginning, to the first bursts of star formation in these tiny galaxies. Even a small dwarf galaxy can create massive stars. When those stars died in supernova explosions in the confined space of a small halo, the effect could have been cataclysmic. The energy released might have been enough to literally blow a vast majority of the galaxy's gas clean out, permanently starving it of the fuel needed to make new stars. This could explain why so many dark matter clumps remain completely dark, solving the missing satellites problem. Furthermore, this explosive removal of mass from the center would have dramatically altered the gravitational landscape. The dark matter responding to this sudden change would have expanded outward, effectively puffing up the central cusp and transforming it into the soft core we observe today. It's a story where the brief, violent lives of the first stars leave a permanent imprint on the invisible scaffolding of dark matter, reshaping it billions of years later. But another school of thought argues that the solution isn't in the astrophysics but in the particle itself. Perhaps dark matter isn't entirely cold and collisionless. What if it has a small but meaningful ability to interact with itself? This is the self-interacting dark matter hypothesis. In the dense center of a dwarf galaxy halo, these rare particle collisions would transport heat inward, causing the dark matter to expand and smooth out the dense cusp, naturally creating a constant density core. This wouldn't require any stellar fireworks. It would be an innate property of the dark matter particle. Alternatively, maybe dark matter is slightly warm, with lighter particles that had too much thermal energy in the early universe to collapse into the very smallest, densest clumps. This warm dark matter would naturally produce fewer satellite halos and ones with fluffier, less concentrated cores, neatly addressing both problems in one go. The dwarf galaxies orbiting our Milky Way are therefore more than just faint companions. They are the battleground where competing theories of dark matter fight for supremacy. Every new star discovered in them, every precise measurement of its velocity, is another piece of evidence in this cosmic courtroom. They are the simplest, quietest places in the universe, and yet they are telling us the most complex and surprising stories about the nature of the vast, invisible web that binds everything together. But if the secrets of dark matter are written across the vastness of the cosmos and buried deep underground, perhaps the most direct path to uncovering them is to try and build it ourselves. This brings us to one of the most audacious endeavors in modern science, the attempt to create dark matter from scratch in the world's most powerful particle accelerators. Imagine trying to solve a mystery by reconstructing the suspect in a laboratory, using the fundamental building blocks of reality to force a hidden particle into existence. This isn't science fiction, it's the daily mission of facilities like the Large Hadron Collider, where scientists are essentially trying to manufacture the universe's most elusive substance. The principle behind this is as brilliant as it is straightforward. Einstein's famous equation, E equals mc squared, tells us that energy and mass are two sides of the same coin. Particle accelerators like the LHC take this to the extreme. They use immense electromagnetic fields to accelerate protons to within a hair's breadth of the speed of light and then smash them together head-on. In the fiery aftermath of these microscopic collisions, the immense kinetic energy of the protons is converted for a fleeting instant into pure energy. And from that energy, new particles can spontaneously blink into existence, particles that weren't present in the initial proton beams. It's the ultimate cosmic alchemy, creating matter from energy just as the universe did in the first moments after the Big Bang. The goal is to recreate the energetic conditions that would have existed in the early cosmos, providing a window into the processes that might have originally produced dark matter. The challenge, of course, is that we're trying to create something that, by its very nature, doesn't want to be seen. A dark matter particle produced in one of these collisions would be completely invisible to our detectors. It would carry away energy and momentum without leaving a single trace, like a ghost silently exiting a room. So how do you look for something that you can't see? You look for the absence of it. Physicists search for collisions where there is a clear and puzzling imbalance in the energy and momentum of the particles that are detected. If two protons collide and the resulting debris shows a significant amount of missing energy shooting off in one direction, it's a powerful hint that an invisible, undetectable particle was created and carried that energy away with it. This signature of missing transverse momentum is one of the most sought-after signs of new physics at the LHC, a silent scream in the data that points toward something unseen. The search is complicated by the fact that known particles, like neutrinos, also leave a similar missing energy signature. Distinguishing a potential dark matter signal from the background of standard model processes requires incredibly complex statistical analysis and a deep understanding of every conceivable way that protons can interact. The LHC experiments, TLRS and CMS, have spent years collecting and sifting through billions of collisions, looking for any excess of these missing energy events that could be the fingerprint of dark matter production. So far, like the direct detection experiments, they have found no definitive signal. But this absence is itself a powerful result, systematically ruling out certain masses and interaction strengths for potential dark matter particles. The hunt at the LHC is also branching out into more creative and indirect strategies. Even if the dark matter particle itself is too heavy to be produced directly, its existence could be revealed through a mediator, a heavier particle that acts as a messenger between the dark sector and our own. This mediator could be produced in the proton collisions and then decay in a very specific way, leaving behind a clear and unusual signature in the detector that wouldn't be possible with known physics. It's like finding the footprints of the ghost, even if we can't see the ghost itself. The ongoing upgrades to the LHC and the planning for even more powerful future colliders are driven by this relentless pursuit. Each new level of energy and intensity allows us to probe deeper into the unknown, pushing the boundaries of what we can create and observe. While the cosmic and underground searchers listen for the faint whispers of dark matter drifting through the universe, the particle accelerators are trying to shout into the void, demanding an answer by brute force, hoping that in the spectacular debris of a controlled explosion, the universe's greatest secret will finally be forced to reveal itself. And so we arrive at the final and perhaps most profound mystery of them all. We've explored the ghostly presence of dark matter, its gravitational grip on galaxies, and the frantic search to identify its true nature. But all of these questions lead to one ultimate cosmic-scale inquiry: what becomes of dark matter in the end? As the universe continues its relentless expansion, driven by the mysterious force of dark energy, what is the ultimate fate of the invisible architecture that has held it together for so long? The answer depends entirely on what dark matter actually is, and each possibility opens a door to a radically different vision of the universe's final chapter. If the standard model of cold, stable, and collisionless dark matter holds true, then its fate is one of profound isolation and loneliness. In this scenario, dark matter particles are eternal. They do not decay, they do not interact, and they do not transform. As dark energy accelerates the expansion of the universe, pushing galaxies apart at an ever-increasing rate, the cosmic web will begin to fray. The connections between the great filaments will stretch and snap. Galaxy clusters, which are the nodes of this web, will become increasingly isolated islands in a rapidly darkening sea of nothingness. Within these island universes, dark matter will continue to hold sway, its gravitational halo eternally binding the remnants of stars and planets. But eventually, even these structures will be pulled apart. The relentless acceleration will overcome even the mighty gravitational pull of the dark matter halos themselves. In the final era, trillions upon trillions of years from now, each individual dark matter particle will find itself utterly alone, drifting in an incomprehensibly vast and ever-cooling void, forever separated from every other particle by an insurmountable gulf of expanding space. The universe's great sculptor will become a collection of infinitely scattered, silent, and passive monuments to a forgotten age of structure. But this bleak, eternal fate is not the only possibility. If dark matter is not perfectly stable, its story could have a much more dramatic finale. Some theories suggest that dark matter particles could eventually decay, transforming into lighter, more familiar particles over cosmological timescales. The rate of this decay would be unimaginably slow, but given the near-infinite future ahead, even the most gradual process would eventually reach its conclusion. Imagine the universe, already cold and dark, suddenly punctuated by the faint, final whisper of disintegrating dark matter. Each decay would release a tiny burst of energy, a final spark in the overwhelming darkness. If this process were to occur, it would represent a fundamental transformation of the universe's composition, slowly converting its dominant invisible mass into a diffuse shower of radiation or other particles, perhaps subtly altering the physics of the far future in ways we can barely imagine. An even more cataclysmic ending could arise from the potential connection between dark matter and dark energy. If these two dark components are not independent but can interact, if dark energy can decay into dark matter or vice versa, the future of the cosmos becomes a story of shifting balance. Should dark matter slowly convert into dark energy, it would effectively be fueling the very force that is tearing the universe apart, leading to a runaway acceleration that would shred structures even faster and more violently than in the standard model. Conversely, if dark energy were to decay into dark matter, the accelerated expansion could one day halt and even reverse as the gravitational pull of this new dark matter begins to dominate, potentially setting the stage for a future big crunch where the universe collapses back in on itself. While these scenarios are highly speculative, they illustrate that the relationship between the universe's two greatest unknowns could hold the key to its ultimate destiny, a final act written in the language of a hidden dark sector. Ultimately, the fate of dark matter is inextricably linked to the fate of everything. Its story is the story of structure itself, from the first gravitational whispers in the early universe to its final standing in a cosmos transformed by time and expansion. Whether it persists as a silent, eternal witness to the heat death, gradually transforms into something new, or participates in a final, transformative dialogue with dark energy, its role is fundamental. Contemplating this ultimate mystery brings our journey full circle, connecting the primordial seeds of the cosmic web to the very last moments of all that ever was or will be. It is a humbling reminder that the invisible majority of our universe, which has guided the formation of galaxies, stars, and planets, will also have the final word in determining how the grand cosmic story ends. And so we find ourselves standing at the edge of a vast and largely uncharted frontier, looking out at a cosmos where the questions far outnumber the answers. From the ghostly gravitational tug that first revealed dark matter's presence to the perplexing diversity of galaxy rotation curves, from the silent aftermath of the bullet cluster to the profound emptiness of the great cosmic voids, each mystery we've explored is more than just a puzzle, it's a doorway. A doorway to a deeper layer of reality, one governed by rules we have yet to fully comprehend. These 25 mysteries are not isolated curiosities. They are interconnected threads in a single, magnificent tapestry of ignorance and discovery. The missing satellites problem and the core cusp dilemma in dwarf galaxies are not separate issues, they are two expressions of the same fundamental tension between our simulations and the real, observed universe. The hunt for a particle, whether in deep underground labs or at the energy frontier of particle colliders, is driven by the same gravitational evidence that maps the dark matter web across the sky. The potential connection to dark energy and the ultimate fate of the cosmos forces us to consider that we may not be dealing with two separate enigmas, but two facets of a single, unified dark sector whose physics operates entirely outside the standard model. Solving any one of these profound puzzles could be the key that unlocks them all. Pinpointing the true nature of the dark matter particle, be it a WIMP, an axion, a sterile neutrino, or something beyond our current imagination, would instantly shed light on why dwarf galaxies lack dense cusps, why some galaxy rotations differ so dramatically, and how this invisible substance sculpted the cosmic web from the universe's infancy. Conversely, a precise measurement of the smallest structures in the cosmos, perhaps by the James Webb Space Telescope or future gravitational wave observatories, could tightly constrain the properties of the particle itself, telling us its mass and how it moves. Yet the most exhilarating and humbling possibility is that solving these mysteries will require more than just a new particle. It might demand a radical rewriting of the laws of physics themselves. The persistent tensions between prediction and observation are the cracks in the foundation of our current cosmological model, hinting that a paradigm shift of Copernican proportions may be on the horizon. We may be on the verge of discovering that gravity works differently on galactic scales, or that dark matter and dark energy are manifestations of a deeper, underlying principle that connects the quantum world to the cosmos. To truly understand the dark universe, we may need to move beyond lambda CDM and into a new territory of physics, one that could revolutionize not just cosmology, but our entire conception of reality. This is the great adventure of our time. Each unanswered question is an invitation to explore, a call to build more sensitive detectors, to peer deeper into space, and to think more creatively than ever before. The cosmic dark matter web is the ultimate cold case, a mystery written in gravity and hidden in plain sight. Unraveling its secrets won't just tell us what the universe is made of. It will reveal the very rules by which it operates, shining a light into the darkness that has for so long been the dominant force in the story of